I'm going to discuss about continuous time martingale. Okay. Before that, is there any problem regarding the previous lectures or so? I don't know whether you have read or not. I have seen only 3-4 students coming to the class. So maybe you thought that everything is free, or there are two cases. Either everything is free, you are thinking, or maybe you know these lectures and all these things. So in that case, if it is the second case, then it is fine. If you know the things, then it is fine. But if you think that everything is free, I think that is not the good way to think of. Okay. Just I'm trying to give a hint that nothing is free in this world. Okay. So it's a give and take policy. Okay. If you give something to the nature, then nature will give you something. And if you hurt the nature, then nature will hurt you in some sense. Anyway, it doesn't matter. So, but I was expecting that since it's a, you know, subject you like it, that's why actually you choose. So it's not the mandatory subject, it's elective subject. That is why people think of that, okay, you like that subject, that is why you choose as elective. And but it seems that just you have to choose some subject and that's why you are coming and so on. Not you, the people who are not coming in that sense. Anyway, also I told you the second option, that maybe you know the subjects and so on. That is very good. It is always good for us that when our students know much, so it is always good. Anyway, so let's start with the continuous time martingale. So that means I have a stochastic process xt. Okay, t is greater equal to 0, and then I have a filtration ft. So it is basically satisfying the usual hypothesis. That means what? So it is a filtration. That means it is basically sigma 0 and also increasing. Okay, so usual hypothesis means it is right continuous. So ft is right continuous. Okay, that means you consider f of t plus epsilon and then take epsilon is positive. So that is my f of t should be something like that as a limit of. You know, so the right continuous from the right actually you are thinking, and also it is increasing right continuous, and the f0 it contains all the p null set. Okay, all the p null set it contains my f0. So in that case actually we say that ft is a usual hypothesis. So generally the thing is that why I consider this right continuity and so on, because here actually there is a concept of stopping time. Already you know the stopping time, but in that case what we consider the stopping time takes values only in the positive integer value or the non-negative integer value 0, 1, 2 and so on. But here since t is my continuous, okay, so for that actually there should require the right continuity of my filtrations to prove that that tau is less than or equal to t, it is ft measurable, and this is equivalent to that t is strictly less than t is in ft measurable. Okay, so for that actually I need the right continuous. So but for your study, think of that my filtration ft is given to you, which is right continuous. Okay, that means this condition hold, and since it is a filtration, it is increasing sequence of sigma algebra. That means if my s is less than or equal to t, then f of s is subset of f of t. This is the always the case here. Okay, like whatever you know for your discrete setup, it is similar thing, but only thing is that I have this right continuity because now you have continuity in your path and so on. So you need these things there. Okay, so like in previous case, like in discrete martingale case, we can also say that when a stochastic process xt adapted to the filtration is a martingale, submartingale and super martingale. So in the same way, actually, we can say there what we can say that we have f of n and then n plus 1. But in this case, I can think of that s and t whenever s is less than equal to t or not. So in particular, what I need the definition. So xt is called martingale again with respect to the filtration. My f of t, okay, it is given to you if the following holds. So again the same three conditions hold, that xt should be ft adapted. Okay, and second we have this integrability condition, no, that expectation of mod of xt, this is finite for every t. Okay, so that constant may depending on t, but as long as t is fixed, that is okay. And third thing is that for s less than equal to t or st less than t, expectation over xt given f of s, this should be my x of s almost surely. So for discrete setup, we put s is equal to n and t is equal to n plus 1. Okay, and similar way actually you can think of f of x any n and then f of n plus k. Is it not? In the same way actually you can use it. So here we try to use that second one. So for the discrete case, what do you have? That say f of xn, or we put as x of n given f of n minus 1. This is actually my x of n minus 1 almost surely. But in a, if I use this again and again and again and use this conditional the tower property of conditional expectation, I can say these things as the expectation of xn given f of k is equal to my x of k almost surely whenever my n is greater equal to k. Is it not? So we try to use these definitions here in a continuous setup. This is exactly same. Okay. So for all s is equal to t, expectation over xt given fs is equal to f of x of s almost surely. And this is for the martingale. Now you can again define the submartingale. So in that case, 1 and 2 holds and 3 should replace by this condition that this is submartingale, so greater equal to xs, no? That means expectation over xt given f of s is these things. And for super martingale, you have this thing. This 3 should be replaced by these things. This is my xs, expectation over xt given f of s. So basically what it says that xt is a random variable now. So the best predictions of xt given the informations up to time s, this is equal to x of s. That is the martingale, means you can interpret the martingale. But in this case, what you have, this is less than equal to x of s almost surely. So this is for the super martingale. Okay. So in this case also you have 1 and 2 conditions should hold for all cases, but only 3 should be replaced by this quantity, then it is a super martingale. So again, like in continuous setup, if xt is a martingale, then expectation of xt is constant. Okay, so as a remark, I can say that if xt is a martingale, then expectation over xt is constant and hence equal to this is expectation of x0. Is it not? But whether the converse is true or not, okay, we will see I have given this in your exercise, means in your assignment there. So the converse of this statement, of this remark, is not true. In particular, what I am trying to say, that if you have a stochastic process xt which satisfy that two conditions 1 and 2, and expectation of xt is equal to say constant or 0 for all t, expectation of xt is constant. So in that case we cannot say that it will be a martingale. Okay, it cannot be a martingale. Okay. Because we need some kind of filtrations property and so on, so that we have the things. Okay, so actually what it says that expectation of x is equal to constant with respect to if it is with respect to its own filtration, then it may not be a martingale. But in general, we'll give you one example that there actually filtration is not given to you. Okay, means if the filtration is generated by only the Brownian component, so means, okay, I'll talk about the Brownian motion later, then actually you will see. So I'll give you one example, kind of sufficient condition with respect to my expectation of xt. So what it says that, so let my xt, this is a stochastic process which has stationary and independent increments. Stationary and independent increments. Then xt is a martingale or sub-martingale or super martingale with respect to its natural filtration if expectation over xt actually is equal to 0, or expectation over xt this is greater equal to 0, or expectation over xt this is less equal to 0 for all t is positive respectively. Okay. So basically proof is simple, because since I have the stationary and independent increments, so from there you will find out whether these things is hold or not. Okay, so how to prove it? See what I have to prove it. I have to show that expectation over say xt given f of s, is it not? This is excess or no? So this part actually I can write down expectation over xt minus x of s and then plus x of s given f of s. Is it not? I add and subtract. So now look at this conditional expectation is linear. Now expectation of xt minus xs given f of s. So this is the increment, and what it says, it's a stationary and increments. Hence actually xt minus xs this is independent of fs, and since it is independent of xs, then what I can write down that expectation over any x given nu, if x is independent of nu, this is same as expectation of x. That is actually we have seen it. So this part I can write down, this is expectation over xt minus xs, and then plus, now x of s is fs measurable, is it not? Because f of xs it's basically a stochastic process which is fs measurable. Okay, so this is nothing but my x of s. And now you see that these things what I can write down. So if my expectation of this is expected xt minus expected xs, is it not? So now what we can have, that this part is same as my expectation of x over t minus s, because it has a stationary increments, is it not? So stationary increment is basically that xt minus x of s, which has the same distribution as x of t minus s, means time homogeneous type of argumentation is there, and then the distribution are same, so expectation will be same. So this is same as the expectation x of t minus s plus x of s almost surely. So now you check that if expectation over xt is equal to 0 for all t, that means this thing is also 0. So in that case, means for the first case, what I have, expectation over xt given f of s is same as my x of s almost surely, is it not? So for the first case, it is a martingale. So second case, what it says that expectation over xt, this is greater equal to 0 for all t. This is the second case. So since this is greater equal to 0, I have this part greater equal to 0 plus xs. So what I can write down, that if we omit that part, so that means what I have, this is greater equal to xs. This, that the left hand side is basically greater equal to only this part. So in this case, I have expectation over xt given f of a, this is greater equal to x of s almost surely. So what I have, basically the submartingalness, is it not? This is for the submartingale. And you see for the third case, it gives you basically supermartingale. So on sufficient conditions, using this example, we have seen that if the process is it has an independent increment, stationary increments, and expectation of xt is equal to 0 for all t, then it is a martingale. If it is greater equal expectation of xt is greater equal to 0, it is a submartingale, and expectation of xt is equal to 0, then it is a supermartingale. So basic idea is that I need independent as well as the stationary increment things. Okay. Okay. So now I put as a remark, we have seen the Poisson process, no? The Poisson process in T. So what is that? Actually, we already seen, no? That summation over characteristic function over that Tn less than equal to T over n greater equal to 1. No? It counts the number of jumps and all these things. But what we have seen there, and then I am considering Ft, which is the natural filtration sigma generated by, so sigma algebra generated by my n of s either 0 less equal to s less than equal to t. Exactly, like similar case whenever we have done it for discretization case. Okay, I am considering the natural filtration generated by my these things. Okay, so in this case, what we have seen that nt, what we know that nt, it has a stationary and independent increments. Is it not? And what we know? We know that expectation over nt, what is that? We have seen that this is nothing but my lambda t, is it not? For lambda positive, for lambda is the intensity, of the interval times, which is basically exponential distributed. Is it not? So expectation of nt is lambda t. So this is basically equal to 0 for all t. Okay. So that means that nt, it's a submartingale. It's not a martingale. Okay. But if you just remember the Dup's decomposition, what it says that if you have a submartingale, then you can decompose it to a martingale part and another is a predictable sequence. Okay, that is for the sequence case, but it can be done it for the continuous setup, but I just try to relate it. So that means if I subtract something, then maybe it is possible to get the martingale. In particular, already we talk about the compensated portion and compensated portion process, no? Okay, n tilde t, we denote that nt minus lambda t. So now you see that n tilde t, it's the independent increment stationary and independent increment, but expectation over n tilde t, this is actually equal to 0 for all t. So my n tilde t is a martingale, okay, with respect to its own filtrations. So whenever I talked about compensated portion process, I told you, no, because it basically makes a martingale. We are subtracting the central things, okay, which is called the compensator, so that it becomes a martingale. Okay, so n tilde t is a martingale. We are not checking all this property, but just looking at this example, because in example it is kind of in abstract setup we have set up. Okay, just to know that whether it has a independent stationary increment or not, and what about the expectations, whether it is positive, it is negative, it is equal to 0. Accordingly, we can conclude about whether it is a martingale, it is a submartingale, or it is a supermartingale of the process. Okay, it's kind of sufficient conditions, not the necessary condition, it's just a sufficient condition. Okay, so in your example actually I asked you to show that something in the variance of my compensated portion process, okay, whether it's a martingale or not and so on. So here, as I told you, nt, yeah, so n tilde t, which is nt minus lambda t. Okay, so now that means my n tilde t plus lambda t is equal to n of t. What I know that it is basically a submartingale. This is basically martingale. Now this one you see that it is at least increasing. So whenever we wrote down the Dup's decomposition, okay, that is in a discrete setup, I know, but what I'm saying that if you just look at the argumentations, so any submartingale we can decompose as a martingale plus some process that is called the predictable process, which is basically increasing. Now issue this lambda t, it is increasing with a0 is equal to 0, so that at t is equal to 0, this process is, if you just denote as my a of t in this setup, a of 0 is equal to 0, at is increasing. Okay, so it is also because of these things actually it is happening. Okay, in particular we have general decompositions for continuous time, that is also called the Dup decompositions for a continuous time semi-martingale. If you have, then actually one can decompose at a martingale, and then the predictable process which is again increasing and so on. We have done it for the discrete case, the proof and so on, but one can do the same thing else for the continuous time process. Okay, but at least see that because of that actually we are having these things. Okay. So now for continuous for discrete setup, already we have something called the Doops inequality, is it not? Then the upcrossing inequality, because upcrossing inequality is important to prove the convergence of discretized or the discrete martingale and so on. No, we want to know whether a martingale convergence or not, converges to a random variable or not. So for the continuous setup, here also we try to know that if I give you say some martingale or martingale in continuous time which has a right continuity path, that is important. So that right continuity path is important. And then can I say that as my t goes to infinity, so because here put n goes to infinity, so you can think of, no, because that is discrete setup is continuous setup, as t goes to infinity, whether it has a limit or not. Okay, so we put as a x infinity is almost surely or no, because martingale convergence theorem gives you only the almost sure convergence, and later on actually you have seen the necessary and sufficient conditions, under what conditions we have Elan convergence also, and there you have seen that you need the process should be uniformly integrable. Okay, so similar results should hold here also. That is actually we try to discuss in this case. Okay, so basic idea is to use all the previous knowledge of discrete type martingale, and then you try to apply here, use the path continuity property of a given process to extend the known result for discrete setup to continuous setup. Okay, so we define that upcrossings, no? Even if here also the same idea, that if you look at the number of upcrossings of a path, then so here actually you have the path, no? There actually we have this say x1 means at n equal to 1, 2, 3 and so on, just the discrete things, but here you have the path. So now if you look at the path and then you consider say the label a and b, and then if for in any ab, so if you see that actually if the number of down crossing or the number of up crossing is infinite, then the process cannot be uh, can't converge to some random variable, is it not? So here we need to define what do you mean by the up crossing there. So because you have discrete and so on, so for any finite time or n, so there you have the finite number of things. So here we try to use that concept here, and then we try to consider supremum of that finite quantities which will cover your interval say 0 to t. So in particular, what I am considering that for any alpha beta is in my R, with my alpha is less than beta, okay, with alpha is less than beta, and f, this is a finite set of 0 infinity. So we define the number of upcrossing. So number of upcrossing we denote as UF over this finite set alpha beta, and then maybe x vector of omega means x of t, something like that, of the interval alpha beta, okay, of the interval alpha beta whenever we restrict the sample path xt on my f by the restricted sample path xt such that t is in my f. Okay, so we define as follows. So see TF is my finite set, is it not? So how I define? We define say tau 1 of omega, which is minimum of T is in my F, T is a finite set, such that my x T of omega is less than or equal to alpha. And then how do define for any j, say 1, 2 and so on, we define recursively sigma j of omega. If you remember, there we define that S1 T1, S2 T2 and so on exactly in a similar manner. Okay, so we try to put it here, sigma g, which is minimum of T is in my F. Okay, so there what we consider, okay, so up to time n we consider that sk k lies between 1 to n. Okay, that n. So now, so that n actually is work for something like it is a point as in your set F. Okay, so this is the T is in F. That means suppose you have say n point, T1, T2, Tn up to T of n is in your set F. Then what we are considering the minimum of T such that this is less than or equal to alpha. Okay, so minimum actually you are considering here, and then I am considering j sigma j. Then tau 1 should less than or equal to sigma j, is it not? Because there we have S1 is less than or equal to T1, and then T1 is less than or equal to S2 less than or equal to T2 and so on. Similarly actually we are having, so we try to put it the minimum test such that my T should be greater or equal to tau j of omega. No, this condition should hold. That is why actually I put it. And my x of t omega, this should be greater than beta. Is it not? Because we initially have, no, this is that case, something like that I have. So now this is negative, this is positive, this is negative, not negative positive, I mean this is my beta, this is alpha, and these points actually we are considering. So there actually we put it up to, this is your up to x of n, all these things. So in between this 0 to n actually we are calculating the supremum of all these things. But in this case, since I have continuous setup, what I consider that I consider any finite set F, and then we look at over that finite set, and then tau of j plus 1, which is minimum of t is in my F, such that t should be greater or equal to my sigma j, and x of t of omega is less than alpha. So now you see this tau j and then sigma j. This is similar to is my sj and then tj, which is your sigma j in a discrete setup case. Okay. And what I consider that UA alpha beta s vector of omega, this I can put it supreme over, and there actually we put, you know, that supreme over all these T1 sk such that this happens. So this is supremum over that u of f, so sorry, the largest j, no, this is the largest j for which always integer, largest integer j, for which my sigma j of omega, this is finite. Okay, so this is the upcrossings of over this finite set. Okay, F along the interval alpha beta, which restricted on, means restricted on your finite set F. So now if your set F is not finite, if it is in any arbitrary set, so then how can I define the upcrossings of my stochastic process xt? So if my I, which is a subset of 0 infinity, which is not necessarily finite, not necessarily finite, so in that case I can consider the similar way, I alpha beta x of omega So you consider any finite set A, okay, alpha, beta, and then restricted on this finite set, where F is my subset of I, okay, and F is finite. And then you took, so now this is the upcrossing over this F for any finite set, and then you consider the supremum over that. So this should be the number of upcrossing, okay, restricted on the sample path T is in on I. Okay. Okay, this is the natural way, no? Whenever you have infinite things, how to define that part? Because you know how to define for the finite set, and then you basically consider all these things and then take the supremum over that. That is the natural way one can define this upcrossing. So this is the case, and always you see this upcrossing things and so on, no? It is basically increasing. The number of upcrossing actually always increasing. If your set is bigger and bigger, it is increasing, then your number of upcrossing should be increasing. In particular, if I consider say I is equal to say suppose 0 to T form, okay, and now if my T then 0 to T plus 1 T2 and so on, so number of upcrossing should be increasing and so on. That is the natural way, you know, because it is same whenever I have this A I, which is basically bigger and bigger, so you can consider supremum. So supremum on a bigger set, it's basically will be a bigger, less than or equal to. That's it. Okay. So now we try to use, this is the definitions of upcrossings and so on. And again here, if the number of upcrossing is finite, then there is a possibility that it will converge. That means as t goes to infinity, the stochastic process xt, it has a limit almost surely. That is actually you can expect. Okay, like in your discrete setup. Before going to that, we will prove the following three things. So I consider my xt, this is a stochastic process with right continuous sample path. Okay. Almost surely, or generally for simplicity we can also consider continuous sample path. Okay, the paths are continuous. T goes to x of t omega, that is basically continuous for almost every omega. Okay, this is the continuous, or in particular the right continuous sample path. And now I am considering say sigma and tau, this is subset of 0, infinity, and alpha, beta, they are real number with alpha is less than beta, and lambda is positive, it is given to you. They are all real numbers. Then the following results hold. In particular, this is called the Dup's inequality. That if you consider that probability of supreme sigma less than or equal to s less equal to tau of xs is greater than equal to lambda, this should be less than equal to 1 by lambda into expectation over x plus of tau. See, in your discrete setup, what we consider that, okay, if it is a non-negative submartingale, okay, if it is a non-negative submartingale, then we have this part. Is it not? So here what I consider here is the following. Oh, okay. I need maybe the I need the submartingale things. So maybe martingale, I can say the not the stochastic process, maybe martingale or submartingale. I miss this word. submartingale with right continuous sample paths. Then this part. So for discrete setup, what we know that okay, this is summation over the supremum over k is less than equal to 1 of xk greater equal to lambda is less than equal to 1 by lambda times expectation of x of n. Is it not? That means n is the highest. So in this case, this tau is the highest. That is why x plus tau, because I have not mentioned here whether it is non-negative or not. So that is why I put x plus. Is it not? This is the x plus things. Okay, because lambda is positive, so these things is greater than is equal to probability of x is greater equal x plus greater equal to lambda, and then I have this part. Okay. And second is, so this is the Doops inequality for the submartingale case, and then we had that approaching inequality. So what we have seen that for the submartingale case, then we have that un expectation of un is then equal to 1 by b minus a expectation of x minus a plus minus x0 minus a plus. No, we have seen it. So similar things actually we can consider here, that expectation over u over the set sigma and tau, okay, over alpha beta of this thing, this the approachings restricted on the time set sigma and tau, then what is that? That is less than equal to 1 by, so this is b minus beta minus alpha, and then expectation over x plus tau, because we put x of n is the highest there, no, there n is the at time n we try to look at the means up to time n the approaching, so that means it is basically tau. So I have expectation of x plus tau plus mod alpha. Okay, is it not? So basically similar kind of things actually we have here. Okay, and C I am saying that is the Doops maximal inequality. We have shown, no, Doops maximal inequality, that if you have a martingale and then p greater than 1 such that x is in LP, but then we have that expectation over supremum over that k is equal to n xn to the power p, this is less than equal to p by p minus 1 to the power p expectation of xn to the power p. Is it not? That is actually we have seen it. So in a, that is the generalizations of this, I can say that is called Doops maximal inequality. What it says that for 1 less than p is finite, expectation over supremum over sigma less equal to t less equal to tau x of s to the power p is less than equal to p by p minus 1 to the power p expectation over x tau to the power p. Okay, because tau is the highest point here in this case. So provided I need that xt is non-negative almost surely for every t positive, and because this should make sense, so this is my x tau, this should be over LP of omega. Okay, so now here why this is so, because for the Doops maximal inequality, if you remember the proof of Doops maximal inequality, there we have used that okay, I have to use the submartingale inequality, is it not? So now whether this is a submartingale or not, this is one question, is it not? So now you see that I have this Jensen's type inequality. If you remember that if I have a sequence xn which is say either martingale or submartingale, and then phi which is convex from say R to R, such that my p of p of xn, expectation over these things, is finite, then my p of xn is submartingale. Is it not? That is what actually we have seen it. So now if you look at the proof here, so the discrete continuous, whatever here we are just using that phi is convex. Okay, phi is the convex, that property, and then the submartingale property or supermartingale property of your xn. So now the same thing else actually we can do it. So if you, what I'm trying to say, that if my xt, it is a submartingale phi r থেকে r is convex, okay, not negative, and then what I can say is that phi of xt is a submartingale, because as I said that here actually we need, so the Jensen's inequality, using this Jensen's inequality we can prove that if xt for a continuous setup also, if it is a martingale or submartingale, and if you consider the phi which is a convex function, then phi of xn is a submartingale, okay, with respect to the given filtrations. So that is the things I am saying, that if you look at the proof of the previous theorem in a discrete setup, one can mimic that proof to show that phi of xt is a submartingale whenever xt is a martingale or submartingale for phi convex. So here actually, because I have this whole to the power p case and so on, so it should be the martingale, no, a submartingale case, because x goes to mod x to the power p, that is convex, and so you can use this theorem to show that it is submartingale, so that you can apply the discrete versions for that, because we know for the discrete case if it is a submartingale, and then we can apply this Dub's maximal inequality, which is exactly in a similar way. Okay, let us try to prove the first part. So as I said, the idea is basically we need to construct certain fj which is a finite set, okay, and it is increasing such that as j goes to infinity, my f of j, it converges to all the points on my sigma tau, the points in that closed interval sigma and tau. You already know that how to do this, that is basically using the dyadic number, no, that kind of the rational approximations and so on. So we'll try to do these things here also, exactly in a similar manner. And then now the path is continuous, in particular it is a right continuous. So if I choose any point t, I can always find a sequence of points from my fj such that it converges to there, and I can consider, since it is a right continuous, I can take from the right side point, and then I can look at the path property of xt, so that my x of t, this is converges to x of tj, where tj is coming from f of j. Okay, so I will write down and then it will be clear. So now consider the enumeration. The counting something like that, sigma is my t0 less than t1, all these things of the numbers sigma tau union sigma tau intersection q. Okay, this is q is basically nothing but the set of rational numbers. Okay, because see why I am considering this thing, because sigma and tau we don't know whether it is rational, irrational, and all these things. So if both are rational, then actually this is fine. Otherwise, actually I need to consider this endpoint. Okay, that is the general issues. and then we said, so now I have this enumerations of this number t0, t1, t2 and so on, and then I said my f tilde, which is union over j is equal to 0 to infinity of my f of j, where f of j is equal to union over I is equal to 1 to j of ti union singleton tau. Okay, so now we see that each fj, whatever I am considering, say this is suppose my sigma, this is tau, I am considering this one, this one, this one, this one, this one is my up to I. Okay, ti in this way. So if you consider say f2, that means basically this is t1 and t2, and so this is suppose t0, this is t1 and t2 and then tau, and then for f3 this is t1, t2, t3 and then tau. So you see this fj is basically increasing, is it not? And the enumerations I have in this point, and it is intersection of q, and then q is dense. So from there actually you see that my f tilde, as it has a dense point of is coming from of my sigma tau, is it not? That means if I consider any t is in my sigma tau, I can always find tj, which is my f of j, such that, okay, that or qj point such that my t converges to tj converges to t, is it not? Because of this q is dense in that state. Okay, so what is my claim? And already you have seen this f tilde. F tilde, this is nothing but that the sigma f tilde I have defined union over that part, so in that sense it is nothing but my sigma tau union sigma tau intersection q, is it not? All the rational points with respect to the and then the endpoints sigma and tau, rational points in all the rational points in sigma and q, and then the sigma and tau, these 2 points. This is my f tilde. So now you see this f tilde is dense in sigma and tau. Okay, that means any point, any element from sigma and tau actually I can approximate via f tilde. Okay, so now if we consider aj, which is all those omega is in my omega, such that supreme over t is in my f of j of x t omega, this is greater equal to lambda. Okay, this is my aj, because now fj, this is basically finite set, fj is a finite state, no? And now in fj, suppose j is equal to say 3, then what are the points? Basically you have basically 4 points in this case. Okay, t0, t1, t2, t3 and then tau, so 5 points are there. And now for each 5 points xt is a submartingale, and hence with all these points if you consider yn, like is basically x of tn, where that t of n is in this f of j, then it is a discrete submartingale, and hence I can use the Dup's submartingale inequality for discrete case, is it not? That is the idea. Okay, so now you see this aj is measurable, that is true, aj is measurable, and aj, this is subset over aj plus 1, it is increasing, is it not? And hence I can define my a infinity, which is all those omega is in omega, such that supernova t is in my f tilde. F tilde is in this set or union of that set of x of t omega, this is greater equal to lambda, and this is same as basically union over j is equal to 0 to infinity of my aj, because it is increasing and so on, so I can define aj in this form. Hence what I can know, so now aj they are basically increasing, and we know that continuity property of a probability measure. So what is that? That actually I can write down that probability of supreme over s belongs to my f tilde x of s greater equal to lambda. This is nothing but my a of infinity. Is it not? This is nothing but my a of infinity. A of infinity. So these things now aj they are increasing, and a infinity is nothing but the lim sup of that set. Is it not? So then what I know that I can send that limit j goes to infinity of aj and then take the probability. Is it not? You can just take these things. These things actually I can interchange. That is how the continuity property of your probability. So this is now limit j goes to infinity probability over aj. Okay, this property I have. Now what about aj? Aj, if you look at this set, so now in aj f of j you have a discrete means the finite set I have, and then all that finite point x say tj, it is a submartingle, discrete type submartingle, so I can apply the discrete time Dup's inequality. So by discrete time Dup's inequality, this is a really nice proof, no? That probability over aj, what I know that this should be less than equal to 1 by lambda, then expectation over that x plus and then maximum of fj, the maximum point of xj, no? So what do we have? Discrete setup, we have something like that, that probability over supreme over k less than equal to n of xk greater equal to lambda, this is less than equal to 1 by lambda times expectation we put as a x of n. That is means basically, so these are the points now. That means I put the maximum of fj point. Is it no? Fj are the finite set and then the maximum of fj as a point. So in this case now each fj contains tau, which is the right end point. Hence this is nothing but 1 by lambda expectation over x plus of tau. Okay, so and then I have this part. So now if you take the limit, this is independent of tau. So what I have, that probability of limit j goes to infinity, probability over aj, this is greater equal to expectation over x plus tau by lambda. Okay, so now as I told you that if I claim that the supremum over t is in my f tilde x of t omega, if this is same as my supremum over t belongs to close interval sigma tau of x of t omega, then we are done. Is it not? Because supreme over the t of set, this is the supreme over these things, it we are done. And this is somehow expecting, no, you are expecting, because x, it has a continuous, right, continuous path. And what is your f tilde? F tilde is nothing but the dense subset of your sigma tau, which contains the endpoints. Is it not? F tilde is nothing but this sigma tau as a set and then union of sigma tau intersection of q, the rational point. So that is our dense actually we know. And then if you look at the right continuity part, so that supremum of this set, whenever t is in your sigma tau, this should be the same as your supreme over t belongs to f tilde of x of tau. Okay, so I will prove only this part, and then later on the similar kind of argumentation later on one can use it. Not this one, the other things actually, but idea is to use the denseness and then the right path continuity property of the process xt. So to prove this claim, so proof of claim, one path is fine, no? in particular your f tilde, this is subset of sigma tau, is it not? So, and then supreme, this implies supreme over t belongs to my f tilde x of t omega, because this is in a bigger set, so it's basically less than equal to supreme over t belongs to my sigma tau x of t omega. This part is trivially fine. So you want to prove the opposite part. So let t belongs to sigma and tau, because this is argumentation is same, just for completeness I am doing only just for one case is to show. So then actually what I say, so then there exists my qj, this is belongs to my f tilde with qj is greater equal to t. Okay, for all t means from the right hand side actually I am considering such that my qj converges to t as j goes to infinity. Hence by right continuity property, okay, so now since this is the case, then actually I can have that x of qj of omega, this is always less than equal to supreme over s is in my f tilde x of s omega, because qj is the point and then I can take from the whole set, so this is greater than these things. So now this part, because of the right continuity property, so right path continuity or right continuity of paths of xt, okay, implies that x of t omega, this is equal to limit j goes to infinity x of qj of omega, and which is less than equal to supreme over s is in my f tilde x of s omega. So this implies this t is fixed, so that means my supreme over t is in belongs to my sigma and tau x of t of omega is less than equal to supreme over s is in my f tilde x of s of omega. This is simple analysis. We have already seen this kind of analysis previously maybe. So combining these 1 and 2, what we have, this implies supreme over s is in my f tilde x of s omega, this is same as supreme over s belongs to sigma and tau x of s of omega almost everywhere. Okay, so that means what? That means now I have this quantity, I have this part, okay, and then probability of aj already we have in these things. So now if you just use there, then what I have, so this implies I have the first Doomb's inequality, or the Doomb's inequality says that probability of supreme over sigma less equal to s less equal to tau x of s greater equal to lambda less than equal to 1 by lambda times expectation over x plus of tau. Okay, so if we say here that okay, it is a non-negative, then we don't need this x plus. X plus always the same meaning, it is a maximum of 0 and x. Okay, so this completes your the first Doomb's inequality. Okay, so part B may be what it says. Now fj, this is subset of f of j plus 1, that is actually we have seen it. Okay, hence if you consider u of fj, this is increasing to u over sigma and tau. Okay, exactly in a similar kind of conditions actually you try to apply it here, because as I told you, no, just how we have defined this u f over finite states, this part I have of crossings which restricted on the finite set fg. Now sigma at tau, then how you consider, actually you consider the finite set fg and then take the supremum. So now actually what it says that if you consider supremum about these things, actually it coincides. So u of fj, and fj is subset of fj plus 1, hence u of fj, this is less than or equal to u of fj plus 1. As a random variable, they are increasing. Okay, so u of fg is increasing to u of sigma tau. U of sigma tau, which is nothing but the number of upcrossings of my stochastic process xt restricted on the sample path t belongs to sigma and tau. Is it not? Okay, so now u of fj, now f of j, which is basically finite set, which is a finite set of points, and then actually by discrete time approaching inequality, by discrete time approaching inequality, why we can consider the discrete time inequality? So if you consider that as a point which is in f of j, then if you consider the associated say y of n, which is equal to x of that t of n, if t of n is in your f of j, then this is a submartingale, and hence actually you can think of the discrete time approaching inequality. And what we have, that expectation of u of fj over alpha beta restricted on these things, this is less than or equal to 1 by beta minus alpha. Then what I have, expectation of x plus, and then the maximum point always we have, so this is maximum over fj and then plus mod alpha. So these things, so now each fj contains the right end point, which is my tau. So this is expectation over x plus tau plus mod alpha by beta minus alpha. Okay, so now what we can consider? So the by monotone convergence theorem, I can say that u fj, this is a random variable, it monotonically increases to u sigma tau. Okay, so by monotone, all are the positives, no? So we can interchange the limit and integration. So by monotone convergence theorem, or I can say that, or in the other hand also I can consider in a different setup also, because this thing, expectation of these things is finite. I have this is in L1, and oh no, here actually cannot the measure by things anyway. So by monotone convergence theorem, what I can say, that expectation over u sigma tau, okay, alpha beta x of omega, this is actually equal to limit is it not, I can take inside that expectation of limit that j goes to infinity u fj alpha beta to x of omega. So now these things is less than or equal to, okay, I have this part, this is exactly same, and then this is limit j goes to infinity expectation over u fj alpha beta x of omega. I just write down this, this is the result of monotone convergence theorem, and then this is less than or equal to what I have, expectation over x plus tau plus mod alpha by beta minus alpha. Okay, this part, and hence what I know, that it is a submartingale xt is a submartingale, and hence actually what I can say, expectation over x of mod tau, which is expectation over x plus tau, this is less than equal to these things, it is finite. So what I have, this implies my expectation over u sigma tau alpha beta to these things is finite. So this is the expectation is finite, but u sigma tau alpha beta over x of omega, this is actually fine, this is non-negative. No, this is non-negative. Hence you see that u sigma tau alpha beta to this should be finite almost surely, because if it is not finite, if it is infinite and the positive thing, so the expectation cannot be finite. So this is finite almost surely. Okay. Okay. So you see that to prove for the continuous setup we are using the discrete results. Okay. So at the end I try to prove the 3-1 C, which is called the Doo's maximal inequality. So in this case what we have given to you that xt is positive almost surely, it is given to you, and x of tau, which is in my LP of omega for p is greater than for some 1. Is it not? It is given to you. So now I set my yj, which is supreme over t is in my f of j of xt. Okay. So now it is clear to you use the previous argument, because my f of j is subset of f of j plus 1 and x has right continuous property. So from there what you can see that yj it will increase, because if j plus 1, this is of the supreme over t is in f j plus 1, so this is basically less than or equal to y of j plus 1, is it not? So yj, this is increasing supreme over, now t belongs to sigma and tau of x of t. It is increasing, and then what we have seen that t belongs to f tilde, which is nothing but the union over aj. F tilde is nothing but union over that f of j, and we have seen in claim 1 that the supremum both are same, is it not? So my y of j, as j goes to infinity, this is now the random variable, it increases and converges almost surely to supreme over t is in sigma tau and xt, we know. And what is my yj? Yj is nothing but supreme over t is in fj x of t. Xt is a submartingale, it's non-negative, and so on we have. And it that yj, it has a discrete points, no, because fj it are the finite sets, so it has only discrete points, so you can use the discrete Doo's inequality, okay, or the Doo's maximal inequality. So by using discrete time Doo's maximal inequality, and what I say the dominator convergence theorem, because this yj I have, what I have to consider that whether yj is dominated by integrable random variable or not. Now if we look at this yj, because for my this case that yjp, expectation over yjp, this is less than or equal to p by p minus 1 to the power p. Okay, let me write here, this is expectation over yjp, this is nothing but expectation over supremum over t belongs to my fj x of t whole to the power p. Now I can use here the Doo's maximal inequality. this is less than equal to p by p minus 1 to the power p, and then expectation of x now plus, so this is non-negative, so this is x of p times maximum of fj, which is nothing but that p by p minus 1 to the power p expectation over x of p tau. Is it not? Now this is in L1 of omega. It is given to you because for tau, x tau is in LP, hence xp is in L1 of omega. So that means I can use the numerator convergence theorem, because now xj yj it increases to here, and then expectation of yj, this is less than or equal to this part. Okay, xj to the power p in L1. So I can use the dominator convergence theorem to conclude. So by dominator convergence theorem, what I can say, that I can pass to the limit here. No, so expectation of the limit things, it should be your supremum over yj, you look at here, and then this is as j goes to infinity, so limit is basically supremum over t is in ft like xt, and that is same as we have already seen by using claim 1, that s belongs to sigma 2 tau, now xt whole to the power p. Okay, this thing should be less than equal to this part. This is measured by p minus 1 to the power p of expectation over xp to the power tau. Okay, this is the Dup's maximal inequality. So now what is useful this Dup's maximal inequality? Already we have seen in discrete setup that if you have a Dup's maximal inequality, then we can have convergence in LP. Okay, that is actually you will use it. So I will stop here, and then the next day I will talk about so-called the martingale convergence theorem in continuous setup. Okay, so for that case, what do we have to use? We have to use basically the upcrossing inequality, like in continuous setup how we have proved it. So here also we try to use that part, because we have seen that the total upcrossing there for any sigma and tau over the interval alpha beta, it is finite, hence you can expect that it should converge. So I'll state that theorem and I will prove next class. That is called the martingale convergence theorem. So as long as you have martingale convergence theorem and using your say Dup's maximal inequality for p greater than 1, we can show that if satisfy the similar kind of conditions, we say that okay, it will converge also in LP. Okay. Continuous time. Okay, what it says there, so let xt be a right continuous. Okay, it is holds for sub-martingale, but I am just putting also the martingale. This holds for sub-martingale case also. Okay, sub-martingale with c, which is equal to supremum over t is positive, x plus over t, this is finite. Now, similar kind of condition, there actually proportional supremum over n, that x plus xn plus is finite. No, we are considering exactly same. Then xt, this converges to x of infinity almost surely, and as t goes to infinity, and x of infinity, this belongs to my L1 of omega. Okay, and here also we will means one can do these things. I am not going into that details, but what it says that if my martingale, if it is say uniformly integrable, then this convergence will be in L1 also. Okay, so the idea is whatever we know, what the main theorem for discrete time martingale, one can generalize it or extend it to the continuous time martingale cases. Only I need that the martingale, it should have right path content or the right continuous paths. Okay, right continuous is enough. We don't need the continuous path. Only right continuous is enough. Okay, in that case. Okay, so I'll stop today, and next I will prove this martingale convergence theorem, and then also we have proved for discrete setup the optional stopping theorem. Here also I will put the optional stopping theorem, and then I will talk about so-called the Brownian motion. You may heard about the name. So one of the important stochastic process, Brownian motion, and few properties of the Brownian motion. So there are many things I cannot do these things. Okay, so I need to stop there, and then it will complete your martingale theory in some sense. Okay, yeah.